Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler, and today we'll be doing Unit 6, Lesson 9 on isosceles trapezoids. So we're coming back to the special type of quadrilateral that started it all, trapezoids. So let's review a little bit about what that basic type of figure is. Now in this lesson we will revisit that original special quadrilateral, the trapezoid. So let's take a look at its definition. A trapezoid. Any quadrilateral that has at least one pair of parallel sides. They could have one or two pairs parallel. All right, now we talked about extensively the idea that all parallelograms are trapezoids. And again, this definition, as we pointed out when we first talked about trapezoids, is strangely enough a little controversial. There will be some states that will say a trapezoid is a figure that has exactly one pair of parallel sides, and others that say that it has at least one pair, which means it could have one or two. We're going with what's called the inclusive definition of a trapezoid, which means it could have two pairs of parallel sides or it could have only one. Now let's play around a little bit in exercise 1 with just this idea of a trapezoid. Exercise 1. In the diagram shown below, ABCD is a trapezoid with AB, segment AB, parallel to segment CD as shown. Letter A. Based on the fact that segment AB is parallel to segment CD, state all pairs of supplementary angles in the figure. All right, well, we've kind of played this game before, so I'd like you to pause the video now and state all pairs of supplementary angles, angles that add up to 180 degrees. All right, well, we know that same side interior angles will be supplementary when they're created by parallel lines. In this particular case, that's going to be angle D and angle A are supplementary to each other, and angle B and angle C are supplementary to each other. All right, so angle A and angle D, angle B, and angle C. All right, now let's take a look at letter B, where I'm going to want you to just speculate on something. Under what condition do you think that angle C would be congruent to angle D? All right, now I've drawn a picture here where hopefully it does not appear that angle C and angle D are congruent to each other, even though they're clearly both acute angles. But there is one situation with a trapezoid where these two angles would be congruent. Pause the video now and speculate on what you think it would be. Well, if you said if AD and BC are congruent to each other, then you would be correct, right? So if AD was congruent to BC, then angle D, or maybe I'll say angle C, would be congruent to angle D. And a little discussion about this. We're going to prove this fact in the next exercise, as we always do. We're not going to just state something and then kind of move on, but we'll prove this in the next exercise. But essentially, you can kind of think about it like this. If I had an isosceles triangle, right, an isosceles triangle, okay, and we know in an isosceles triangle that the base angles are equal, and then we came along and we sort of sliced it with a parallel line, okay, thus creating this figure, right? What we would then have is exactly that situation. I mean, poorly drawn, but we'd have exactly that situation, which is we would have this side parallel to this side congruent to that side, and these two base angles would continue to be congruent. As well, these two angles would also be congruent, and we'll prove that in the next exercise as well. Speaking of which, let's move on and talk really about the subject of the day. Let me switch this back to blue real quick. Let's talk now about what are known as isosceles trapezoids. We will now concentrate on a special type of trapezoid that arises often in real-world settings. You see these all the time, and they are known as isosceles trapezoids. Now, these are very specific types of quadrilaterals, so let's take a look at their definition. Any trapezoid that has exactly one pair of parallel sides and the two opposite sides that are not parallel are congruent. All right, so in other words, a trapezoid in general could have one pair of parallel sides or two. An isosceles trapezoid is going to have only one pair, and then the other pair of sides, the ones that are opposite of each other, are going to be the same length. And so that word isosceles really kind of in math means same length. An isosceles triangle is a triangle that has two sides that are the same length, and an isosceles trapezoid is a trapezoid that's got only one pair of parallel sides and the other two sides, the non-parallel ones, are the same length. So let's take a look at exercise number 2. In the diagram shown, EFGH is an isosceles trapezoid with segment EF parallel to segment GH and segment EH congruent to segment FH. We wish to prove that angle EHG is congruent to angle FGH and angle HEF is congruent to angle GFE. To do this, side EF has been extended through F to point I such that HE is parallel to GI. Okay, there's a lot going on there, so let's just make sure that we understand the thrust of what we're going to do in this exercise before we go ahead and do it, right? So just hone in on the figure EFGH. This is that isosceles trapezoid we were just talking about. So EF is parallel to GH, and side HE and side GF are the same length. Now, just as we speculated in the last exercise, what we want to do here is we want to really prove that this particular angle is congruent to this one, and this particular angle is congruent to that one. And it's a little bit tricky to actually do. The way that you have to do it is similar to what we did when we did our lesson on the midpoints of a triangle. We're actually going to extend side EF all the way to some magical point out here, I. We're going to draw GI in, and we're going to extend that far enough so that GI is parallel to HE, okay? And using this figure now, we're going to be able to prove that this angle here, angle EHG, is congruent to this angle here, angle FGH. So let's do that. Letter A. What type of figure is EIGH? Explain. All right, well, what type of figure is EIGH? So that's EIGH. Don't do it just based on looking at it. Do it based on what you know right now about the figure. Well, simple enough. It's a parallelogram, right? And it's a parallelogram for one simple reason. EI is parallel to HG, and HE is parallel to GI, right? So it's a parallelogram because it has two pairs of parallel sides. And of course, the great thing about having a parallelogram in this figure is that we know all sorts of stuff about parallelograms after all the lessons we've done on them. Now, let's keep going. All right, letter B. Why must triangle FIG, or triangle FIG, be isosceles? Mark its congruent sides. Mark its congruent base angles. So there's a bunch of things going on in letter B. The first thing that we'd like to do is figure out why triangle FIG must be isosceles. So pause the video now and think about how you could sort of justify that FIG is isosceles. Well, think about what we know. This is really cool. We went in knowing that EH and FG were congruent, right? So do kind of like a mini proof here. EH is congruent to FG, and that was just sort of given. Right? We're not going to draw our giant T-table proof. But what else do we know? We also know that EH and IG are congruent, right? So EH must be congruent to IG because they are opposite sides of a parallelogram. Hello. Right? So we know that these two have to be congruent. Right? Well, now it's easy. If EH is congruent to FG and EH is congruent to IG, then clearly FG must be congruent to IG. And if you want a reason, you could always say substitution, right? But it's sort of obvious, and it goes to this plain fact, right? If two segments are congruent to the same segment, then they must be congruent to each other. So right now we know that this particular triangle is isosceles, right? And we know therefore that its base angles must be congruent to each other. So those two angles are congruent to each other. Awesome. Let's take a look at letter C. Now, before we answer letter C, what I'd like to do is I'd like to mark these angles. Of course, you've just got the one diagram. I keep having it reproduced. So I'm just going to mark those two base angles being congruent. Now, letter C. Why must angle IFG be congruent to angle FGH? So now we're asking, right, why does this angle, IFG, have to be congruent to that angle? Pause the video now and see if you can write something down concerning that. All right, and what I'm going to do right now is I'm going to mark those congruent angles, right, like this. And of course, those angles have to be congruent because they're alternate interior angles created by two parallel lines, right? We know that EI is parallel to HG, and those are alternate interior angles created by parallel lines, because they are alternate interior angles created by parallel lines. Fantastic. Okay, so let me just move this up for a second. Let me mark these two congruent angles, and then these two congruent angles. All right, and now let's take a look at D. Why must angle EHG be congruent to angle FGH? All right, so this is one of the things that we were trying to prove. We're trying to prove that EHG, this angle, is congruent to angle FGH, right? We want to prove that those two base angles of an isosceles trapezoid are congruent. But why is that given everything that we see right now on the picture? Pause the video and see if you can answer that. All right, well, this is cool. Watch this chain of reasoning, right? I want to prove that this angle is congruent to this one. Well, I know that EIGH is a parallelogram. So what I do know is that angle EHG must be congruent to angle FIG, angle Fig, because they are opposite angles in a parallelogram, right? We know that opposite angles in a parallelogram are congruent, right? So I can say that that angle is congruent, right? That angle is congruent to that angle. But now we basically have it, right? That angle is congruent to that angle is congruent to that angle, right? And therefore, and since that angle is also congruent to that one, these two have to be congruent to each other. So let's write it all out, right? We know that angle FIG is congruent to angle IFG, but angle IFG is congruent to angle FGH, right? And therefore, since angle EHG is congruent to angle FIG, that tells us that angle EHG is congruent to angle FGH. My apologies for that last little piece. And you can really see it in the way that we've marked the diagram, right? I haven't put any extra arc marks here or any extra dash marks, right? This was congruent to this because that's an isosceles triangle. This one was congruent to that one because those are alternate interior angles, right? And then this one is congruent to that one because they're opposite angles in a parallelogram. So ultimately, this has to be congruent to that one through substitution. All right, so we now have these two angles congruent to each other. Let's come all the way down here and mark that. This angle is congruent to that angle. And the final piece, why must angle HEF be congruent to angle GFE? So the last little piece is that we want to just explain why this angle must be congruent to that one. Pause the video for a moment and think about why that would have to be true. All right, well, this takes us all the way back really to exercise number 1 where we talked about supplements, right? We know that angle EHG is supplementary to angle HEF. And we know that angle FGH is supplementary to angle GFE, right? So, right, this angle is supplementary to this one, that angle is supplementary to that one, and just think about it for a second. Let's say these things were both 50 degrees, right? Then both of these would have to be 130 degrees, right? So at the end of the day, angle HEF must be congruent to angle GFE because they are supplementary to two congruent angles. Right? So supplements of congruent angles must be congruent themselves. And that makes all the sense in the world, right? If that is let's say an 80-degree angle and that's an 80-degree angle, then both of those have to be 100-degree angles, and therefore they must be congruent to each other. Supplements to congruent angles must be themselves congruent. So do complements, all right? And we talked about that a long time ago, I think even in unit number 1. All right, now at the end of the day, right, after all of that, we bring you to isosceles trapezoid property number 1. The non-supplementary angle pairs in an isosceles trapezoid are congruent. In other words, base angles are congruent, okay? And it's pretty easy to really kind of understand that idea, right? Because what an isosceles trapezoid really kind of is it's really just an isosceles triangle that's kind of had its top cut off by a line that is parallel to its base, okay? And it's very important because, again, isosceles trapezoids come up in all sorts of things, especially when you look at engineering. If you look at any kind of a truss system or a bridge or sort of like the rafters in a house, you'll see isosceles trapezoids all over the place. And knowing that those base angles are equal, especially the two that are down here, is exceptionally important. Let's take a look at a very easy, I think, or a very straightforward word problem based on that idea. Exercise number 3. In isosceles trapezoid QRST shown below, segment QR is parallel to segment ST, and segment RS is congruent, to segment QT. If the measure of angle Q is 54 degrees more than the measure of angle T, then find and label the measures of each angle of the trapezoid. All right, so I just kind of want to mark some things up, right? I know that this is parallel to this. I know this is congruent to this, okay? And I've been told that the measure of angle Q is 54 degrees more than the measure of angle T. And of course, anytime you see something like that, it's pretty natural to say, let the measure of angle T be equal to X. Let the measure of angle Q equal X plus 54, right? And those are right here, X and X plus 54. Now, without even knowing that this is an isosceles trapezoid, I can now set up an equation to let me solve for x, because these two angles in any trapezoid would end up being supplementary. So I can write down x plus 54 is equal to 180. Nice algebraic equation to solve. Just collect some like terms. Let's subtract off a 54 from both sides. That's going to leave me with 2x is equal to 126. I'll just now divide both sides by 2, and x will be equal to 53 degrees. Nope, not 53 degrees. Let's see if I can do my division right in my head. 63 degrees. Awesome, right? And now I can fill in all the other angles, right? Because the measure of angle T now is 63 degrees. Of course, 63 plus 54 is going to be 117 degrees. So that's going to be 117 degrees. This is going to be 117 degrees. And this is going to be 63 degrees again. 107? 107? Is it 107? What am I doing wrong here? No, it's 117. Maybe it's wrong on the answer key. Because, yeah, definitely 63 plus 117 is 180. Sometimes we get our answer keys wrong. Sometimes I get it wrong up here. You all know that. We all make mistakes. We just hope that we catch them before they make it onto the permanent video. Okay, let's keep going. Let's play around a little bit more with isosceles trapezoids. Now, the diagonals of an isosceles trapezoid are also important. Isosceles trapezoids have another, what I would call, symmetric property that is probably not surprising. And let's take a look at it. Isosceles trapezoid property number 2. The diagonals of an isosceles trapezoid are congruent. They are the same length. Now, I want to point something out before we prove this, because you know we're going to prove it. There's only one other special figure so far that we've had that's had diagonals that are the same length, and that's the rectangle, right? And it's important to note this, because if you ever see something, a trick question that might say, oh, a quadrilateral with congruent diagonals must be what, right? It doesn't have to be a rectangle. It could also be an isosceles trapezoid. So let's take a look at exercise number 4 and prove what probably seems pretty obvious, which is when you have an isosceles trapezoid, its diagonals have the same length. Let's take a look. Given ABCD is an isosceles trapezoid with segment AB parallel to segment CD and segment BC congruent to segment DA, prove that segment AC is congruent to segment BD. All right. Well, I'd like you to pause the video right now and think about how to do this proof and see if you can get the proof down. We've done so many proofs like this in the quadrilateral unit, and this one's relatively easy, okay? See what you can do. Pause the video now. All right, well, here's why it's relatively simple. Okay, we know that these two sides are congruent. We know that these are parallel. And there may be multiple ways to do this proof, right? But at the end of the day, right, I'm trying to figure out that this segment is congruent to that segment. And almost always, when I'm trying to get two segments congruent, I'm going to first try to get two triangles congruent, and then use CP/CTC to then conclude that two parts of those triangles are congruent. Now, which two triangles am I going to try to get congruent? Well, let me just do a highlighter really quick, because I think that that's always pretty helpful when we're looking at something like this. If I take a look at this triangle, and let me move it out here, and if I then take a look at a triangle that I highlight in a different color, this particular triangle, all right? What do I know about those two triangles? Let me go back, right? One thing I know immediately is I know that these two side lengths are the same length. Whoops, I went into green, which is always dangerous when you have a green screen going. All right, so I know that that side and that side are congruent. Because it's an isosceles trapezoid, I know that its base angles are congruent, so I know that those two are congruent. And finally, this is a shared side. so I know that it's congruent to itself. And therefore, that particular triangle, which is ADC, will be congruent to that particular triangle, which is BCD, by the side-angle-side triangle congruence theorem. Now, side note, you could even bring in the parallel lines at this point, okay? And that would actually allow you to conclude that that angle is congruent to this angle, and you could kind of go about getting that entire like angle side angle piece. But the most straightforward way is side angle side in my mind. And of course, once you have those two triangles congruent, you can then state that these two are congruent by CPCTC. All right, let's see how that plays out. First things first, BC is congruent to DA and AB is parallel to CD. Easy enough, those are my givens. Then we've got angle ADC is congruent to angle BCD. That's because base angles of an isosceles trapezoid are congruent. Make sure you don't say base angles of an isosceles triangle. Now we can bring in that reflexive property. DC is congruent to DC, or CD is congruent to CD. That's our reflexive property. We can now state that triangle ADC is congruent to triangle BCD by the side-angle-side congruence theorem. And finally, we can conclude that AC is congruent to BD by our friend CPCTC. That seemed to take a little while to come up. Little pause there. Anyhow, right, this is a nice, simple CPCTC proof based on the fact that we've already proved base angles of an isosceles trapezoid are congruent, right? But it's a simple enough CPCTC proof then to prove that the diagonals of an isosceles trapezoid must also be congruent. Awesome. Let me pause the video right now, or you pause the video right now and write down any of these statements and reasons that you may have missed. All right, let's move on and take a look at our last little piece. We can work with isosceles trapezoids in the coordinate plane. Keep in mind that for an isosceles trapezoid, this is different than a trapezoid, for an isosceles trapezoid, only one pair of sides can be parallel, and the other pair of sides must be congruent. So let's take a look at exercise number 5. Quadrilateral ABCD is shown with vertices at A, -4, 4, B, 0, 8, C, 9, 5, and D, -1, -5. Prove that ABCD is an isosceles trapezoid. All right, so to prove it's an isosceles trapezoid, we have to really do two things, or maybe three depending on how you count things. All right, one thing that we have to do is prove that it has only one pair of parallel sides. All right, and the second thing that we have to do is prove that the two sides that are not parallel are the same length. So let's first try to prove that it has only one pair of parallel sides, and we're going to do that by calculating the slopes of all 4 sides. All right, now I know based on the picture it appears that AB is parallel to CD and AD is not parallel to BC, but I really do need all 4 slopes. So let's do that a little bit. Let's start off together and calculate the slope of AB. And then I'll have you calculate some slopes on your own. So for AB, our slope is going to be 8 minus 4, all divided by 0 minus -4. That's going to be 4 divided by 4. And that's nice. I like a slope of 1 or caret or whatever I was about to draw. All right, so I've got my slope of AB. I'd like you to now calculate the slopes of BC, CD, and DA. Go ahead and do that. All right, here we go. So now, for BC, my slope is going to be 5 minus 8, all divided by 9 minus 0. That's going to be -3/9, which is -1/3. Let's now do CD. That slope is going to be -5 minus 5, all divided by -1 minus 9. -5 minus 5 is -10. -1 minus 9 is also -10, and that's a slope of 1. And finally, DA, that's going to have a slope of 4 minus -5, all divided by -4 minus -1. That's going to be +9 divided by -3, and that's -3. Okay. Now, what's important about this, obviously, is that you see two segments that have the same slope. So immediately I can say that AB must be parallel to CD because slopes are equal. And I can also say, and need to say, that BC is not parallel to DA, my other pair, because slopes are not equal. All right. So what I've done here is I've established that this is a figure with exactly one pair of parallel sides, AB and CD. Without doing all four slopes, for all I know, I could be dealing actually with a classic parallelogram right now, right? For all I know, maybe BC and DA are parallel to each other. I get it, I got the picture, they don't look parallel. But the point in geometry is to be able to prove things either using logic or using coordinate geometry. Now, to make sure that it's an isosceles trapezoid, what I have to do is I now have to take my two sides that are not parallel, those are BC and DA obviously, and I have to find their lengths. All right, so let's now find the lengths of BC and DA. Trying to figure out the best way to do this. I think I need to write down my coordinates again. So I'm going to write them down right here before they disappear from the page. A is at -4, 4. B is at 0, 8. C is at 9, 5. And D is at -1, -5. And again, what I need are the lengths of BC and DA. Let me extend this a bit. All right, so BC. Let's figure out its length. Okay, so using the distance formula, we're going to have 9 minus 0 squared plus 5 minus 8 squared. That's going to be the square root of 9 squared plus -3 squared. That's going to be 81 plus 9, and that's the square root of 90. Now, I could simplify the square root of 90 as the square root of 9 times the square root of 10, but there's no absolute imperative that I do that. All right? In fact, all I want to do is prove that BC and DA have the same length, so let's now go on and figure out the length of AD or DA, depending on how you want to look at it. All right, so the length of AD, let's do -1 minus -4 squared plus -5 minus 4 squared. Lots of negatives here, right? -1 minus -4 is +3, that I'll have to square. -5 minus 4 is -9, which I'll square. And then 3 squared is 9, -9 squared is 81, and that's the square root of 90. All right, so now I can make a concluding statement, which I always kind of want to do when I do a proof. I can now say that ABCD is an isosceles trapezoid because it has exactly one pair of parallel sides and the other pair is congruent. Okay. Now, even the idea of an isosceles trapezoid is a little bit disputed, let me say it that way these days, because there's a dispute in terms of what makes something a trapezoid. Is it exactly one pair of parallel sides? Is it at least one pair of parallel sides? But this is the classic way that an isosceles trapezoid is defined. And because the figure is so important in terms of structures, physics, engineering, all of that kind of stuff, we felt it was important to cover that topic. All right, so let's wrap this up a bit, right? Isosceles trapezoids, right? Trapezoids, any figure that have at least one pair of parallel sides. An isosceles trapezoid is a trapezoid that has exactly one pair of parallel sides, and that other pair of sides must be the same length. Because of the symmetry of isosceles trapezoids, there's all sorts of great properties that they pick up, including the fact that their base angles are congruent and their diagonals are congruent. We'll see isosceles trapezoids kind of rise up here and there for the rest of the course. For right now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.